idea of the hill analogy. Said that Kirchhoff's loop rule and ladder, and then we had a 6-volt drop, the slide, and then we had a 10-volt drop, and then an 8-volt drop. Bring it back. Okay. This will always happen. Okay, whatever the voltage in is equal to the total voltage drop. Okay, now, in your lab, page 2, top chart, let's ignore these two. Okay, just a simple circuit. So from A to B, you had a really small number, like 0.002 or something like that. Between these 2 points was a wire. Best case scenario, we're assuming that there's no energy taken. But in reality, there's a little bit of resistance in the wire, so it actually decreases a tad bit. There's a little bit of a voltage drop across the wire. Then you get to the resistor, B to C, and there's a big drop. It'd be like, huge drop. Okay with that? There's one resistor. And then we went from C to H, and there was a small drop, like 0.02, meaning there was a little bit of resistance, a little bit of energy taken. And then we got from A to H, and it was like huge because we're now back at a voltage gain. Okay? The hope is these three added together gave you this. Or real close to that. Yes? No? Okay? I'm trying to show you, give you a conceptual understanding of what you're doing. I don't want just numbers like, oh, look, they add up, yay. Okay, but like, why do they add up? It's conservation of energy. Good? Okay.
Conversation. About physics.
So I ended up.
I'm sorry.
It'll be okay.
And then when we first started sleep, I basically if you add
Oh, yeah. I read the prologue first chapter.
we didn't use it.
Correct answer is? Correct answer is B. Okay. To make connections with our hill analogy, or Kirchhoff's loop rule. Voltage gain equals voltage drop in a loop. That's a loop. Voltage gain equals voltage drop. That's a loop. It's a separate loop. Okay. From the hill analogy, it's like doing this. And then here, we just have a separate slide. So we got options. Okay with that? I could draw this, I could wire this circuit like this. This would be a waste of wire, but independently hooked up. If I take this out, this one could care less. Is not affected at all. This one is hooked straight up to the power supply, so whatever the voltage across this is, that's the same voltage across this. Like that. Okay, here's the other factoid. So yesterday I told you that current is the same in a series circuit. Second factoid, must be memorized. The voltage is the same in a parallel circuit. Current is the same in a series, voltage is the same in a parallel. Okay? You see why voltage is the same. Independently hooked up. Okay? Okay. So, in my water tower analogy, kink with a hose. If I would add another kink here, that would be adding a resistor in series. How would I draw another resistor in parallel with this analogy? Thoughts? Brainstorm. Got anything? Lawrence, you got something? We'll do another hose. Okay, so if you turn this on and off, this one doesn't care. Totally independently hooked up. You have the same amount of pressure. Okay with that? Independently hooked up. Let me give you this disclaimer. Yesterday's lab, I intentionally gave you identical light bulbs. They all had the same resistances. Okay? These are different light bulbs. Does that make sense? Tell your neighbor. What do you think? Why you think? Okay. Correct answer is A. Good with that? Okay. We can apply Ohm's law to individual. This has the same voltage. The resistance is lower, therefore the current is higher. Good with that? Okay. It does not matter where it comes in, like how far away it is from the battery. Okay? Tell your neighbor what you think. Sorry, premature telling you to talk to each other. How we doing? Got something? What do you say? Correct answer is A. One way to do it is what we just talked about. So we talked about which one ever has the least resistance is going to have the most current, and then power is equal to current times voltage. Voltage is the same as most current has the most power. Okay. Another way to do it is the shortcut. I'm going to use this equation because voltage is the same. So as resistance goes down, power goes up. Good with that? Thumbs up when you got an answer. Tell your neighbor what you think. Correct answer is. Got it. Tell me. You don't have to tell me. What's your guess? Correct answer is A. Okay, check it out. You can do these independently. So you have 12 volts equals current times 2 ohms. And this one, 12 volts is equal to current times 3 ohms. And you can do them independently. Good with that? So your name, what did you think? What do we think? Okay. So, may I introduce to you a junction? That would be a junction where current has a choice. Go this way, or it can go this way. Like add a positive into negative. Okay. So the junction rule says the current going in at a junction has to equal the current going out of a junction. Okay. So here we have 6 amps. Here we have 4 amps. So the current going into this junction must be the sum of what goes out. Correct answer is E, 10 amps. Okay, you see that? That's different than in series. This is parallel. Okay. Good with that? Questions there? Just told you that. All right. Okay, so this is an analogy. I've got a second analogy that might be a little more relatable to water towers. It's Christmas time at Walmart. You are the store manager. Your objective is to get people in and out of Walmart as many as possible. Okay? The bottleneck to that process are the checkout lines. The checkout lines are your resistors. You okay with that? Okay. To add a resistor in series, that would be like saying, hey, you gotta go through the checkout line and then you have to go to customer service. That would not help the process. But if you added if you opened up another checkout line, would that help or hinder the flow of people out of Walmart? Tell your neighbor. That question, to answer that question and answer this question. They're the same.
It's taking more time to do this long line.
Okay, what do you say? What's gonna happen, the rate at which water is draining if you added another pipe with kinks in it? Increase, decrease, stay the same? We're gonna increase how fast we can drain the water tower. If I added another checkout line to Walmart, I'm helping people leave Walmart faster. There's more people exiting Walmart every minute or whatever. You okay with that? Okay. So this is an analogy to adding a resistor in parallel. Neighbor, what you think? What do you say? Got one vote for A. Couple votes for A. Correct answer is A. We are increasing the amount of current because we've given current another path. So like independently they're hooked up. So like that the battery needs to like power that one, needs to power this one, needs to power this one independently. Okay, added another hole to our water tower. We've added another checkout line to Walmart. There's more current being drawn from the battery. We're going to kill the battery faster with this arrangement than we are with that. Yes? No? You okay with that? Okay. Thumbs up when you have a guess. Converse. Correct answer is okay. Let's look at Ohm's law and look at the totals. That's what I'm asking for, yes? What happened to the total voltage? It stayed the same, still connected to the same battery. What happened to the total current when I added a resistor in parallel? We said increase. Therefore, what must be true about the resistance? It has to, what? I added a resistor and the total resistance decreased? That's what the math says. Okay. Conceptually, are you helping or hindering drain Walmart when you add another checkout line? You're helping. The total resistance decreased. The bottleneck that getting people out of Walmart just got a little wider. You added another hole to your water tower. More water is flowing out. The total resistance to drain the water tower is now decreased. You okay with that? I know it's counterintuitive. But you see why when you add another resistor. Think of it as adding another path for current to flow rather than adding a resistor. Okay? All right. So mathematically, the total resistance in parallel is equal to 1 over, the total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Yes, from the pre-quiz? Okay? So, check this out. Total resistance is equal to 1 over 12 plus 1 over 6 plus 1 over 4. I made this really easy for myself. Okay? That's the same thing as 1 over 12 plus 2 over 12 plus 3 over 12 gives me 6 over 12. Okay? So 1 over the total resistance is equal to 1/2. Good? That's not the answer. Okay? Don't stop there. That's equal to 1 over the answer. So find the reciprocal for both. Total resistance is equal to 2 ohms. That's your answer. Okay? Good with that? Let me show you a really cool button on your calculator. Pull out your calculator. You're looking for x to the -1, or inverse, or 1 over x. Everybody see it? X to the -1, 1 over x. Yep. Good. Okay. Check this out. As soon as you get something. Oh, 1 over. Oh, I see. Good. Yes. 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 Good.
I don't know. I won this one, so I got this one. I only keep that one. Two calculators.
Yeah, check it out. Ready? Watch this magic. 12. This button. Plus 6. This button. Plus 4. This button equals 0.5. Don't stop there. Hit that button again. Equals your answer. It's just that easy. But, folks, this is going to be a popular wrong answer. Choice A, 1/2. Okay? Don't stop prematurely. Good? Okay. All right. I'm going to add an 8 ohm resistor to that circuit. Find the total resistance. Go. I just added an 8 ohm resistor. Find the total resistance, the equivalent resistance.
Basically exactly the same. It's just, and
Is it just
our whatever is whatever. Yeah.
Okay. What'd you find? 1.6. Everybody get it? How does that compare to 2? Last, we added a resistor, we decreased the total resistance. Everybody good? Proof of concept. Good? Next question. Hang tight, hang tight. Tell your neighbor. Correct answer is A. If you were tempted to put B, that's because you forgot to find the reciprocals. Okay? Conceptually, ready? Here's the takeaway. You can do it on your calculator, that's great. The total resistance of a parallel circuit is going to be less than the least resistance. the total resistance is gonna be less than the least resistor. Okay? Here's my Walmart analogy. You got MVP checkouter of the year. Beep, 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 beep. Just like flying. You've got your grandma's best friend who just got employed by Walmart. Lot of resistance. She doesn't know what she's doing. She wants to show you all the pictures of grandkids. Like, oh my goodness, you would not want to go in that line. However, is she helping or hindering drain Walmart? Like the fact that she is open, are more people leaving Walmart per minute than if it was just the employee of the month? Yes, you would not want to be in that line. I give you that. But there's more people leaving Walmart because there's another checkout line open. You okay with that? Thumbs up when you have a guess. Tell your neighbor.
I think one is the rate of
What do you say? Okay. Between 2 and 3, which one has more current? 3 has more current because this has less resistance. Okay? The current going through here, current going here is the same as the current going through here. You ready with that? Okay? So, here, I've got current flowing through here. Got current flowing through here. At that junction, I have to have a lot of current going through there. Okay with that? At this point, current has a choice. You can go this way or that way at that junction. Good? conversation. What do you say? Correct answer is E. Okay. We just had this conversation. Okay, so check this out. 3 has to equal to 4. Okay? There is no other path for the current to go. What goes in? There is no junction. You all right with that? You can't have more going in than coming out. Then there'd be flooding. You all right with that? Can't be more leaving than going in. It's the same amount of current. Okay? We have that same conversation with 2. Like it's the same amount of current going through here. Okay? 1 is the combination of 2 and 3. 5 is the combination of 4 and we'll put another 2 here. Yes? All right with that? Questions there? Okay, last question. Tell your neighbor what you think.
No response.
Okay. Here's a pre-question. 1, 2, 3. Where's the more current? 1, 2, 3. 3. And then 1, and then 2. Yes?
Yes.
Okay, individual resistors. Now, 4. How does that compare to 3? Which one's has more current? 3 or 4? 4, because 3 flows into, and 2 flows into 4. Does that make sense? Current in 2 plus the current in 3 gives you current in 4. Correct answer is C. Good? No homework. Enjoy your weekend.